First, let's go over some notation and definitions. In these slides, a random variable is denoted by a capital letter, such as capital X, and a specific instance of that random variable is denoted by a lowercase letter x. A probability density function, or PDF, for some random variable x with a parameter set, alpha, so that's a vector of parameters, is denoted f sub x. For example, a common PDF is the uniform distribution, where the random number u is a number between 0 and 1, with specific instance lowercase u, that's shown in the dotted line here. And we often symbolize that a random number is sampled from a certain distribution with this tilde notation. For example, here we have that u is sampled from a uniform unit distribution, meaning that uppercase U starts from 0 and ends at 1. Now, the height of this rectangle is also 1, and we know that because for a valid PDF, we require that the integral from negative infinity to infinity of f of x dx is equal to 1. From the PDF, we can also obtain the cumulative density function, or CDF, which is denoted by a capital letter f sub x. The probability of the random variable x being less than or equal to some lowercase x, which is a specific instance of x, is computed by the integral from negative infinity to x of the PDF f of x. In this equation, tau just represents a dummy variable. Note that because the total area under the curve of the PDF is equal to 1, the limit of f of x as x approaches infinity must also equal 1. It generally asymptotically reaches 1. When employing the Monte Carlo method, it's necessary to obtain random samples from a given PDF. For example, in the fission model, one of the random variables would be a neutron scattering angle. The way that we choose a random sample is using what's called inverse transform sampling, and here's the procedure. So if x is a random variable that has a CDF f of x, then a random sample from the distribution lowercase x can be obtained in this way. So first of all, we draw a sample from the unit uniform distribution, lowercase u. That, remember, has a value between 0 and 1. We then set x equal to the value of f of x inverse evaluated at u. In the case where we don't know analytically what the inverse is, we can also use the infinitum function. To illustrate what this means, consider the following CDF. As you can see, it starts here at 0 and goes up to 1 asymptotically as x approaches infinity. Let's say that we produce a sample lowercase u, which is between 0 and 1. And because f of x is limited between 0 and 1, we can obtain the corresponding value of x, which is just f of x inverse evaluated at u. The first example that we'll go over is a simplified fracture analysis model, and we'll look at rod breaking. Let's say that we have a glass rod of length L, and suppose that the rod is exposed to some uniform vibration. So let's say it's on the ground and it's vibrating on the ground. And let's say that it breaks into two pieces initially, and then it breaks again. And these breaks occur randomly. What is the expected length and standard deviation of the length of the final pieces? To simplify the problem, we'll look at this in one dimension. So let's say that capital L is the total length of the material, and at some time, the first break happens, and let's call that a distance x. So x is our random variable. The random variable x is selected from a uniform distribution, f of x, which is shown here. So the value of little x can occur anywhere between 0 and capital L, and because it's a uniform distribution, the height of f of x is 1 over L to make sure that the area under the curve is equal to 1. After the first piece breaks, the second piece breaks, and let's call that a distance little y. The location of the second break y is dependent upon the location of the first break x, because now the distance y can only be between 0 and x. What I'm showing on the right is the conditional probability density, f of y given x. In this case, the maximum value of y is x, so therefore the height of the PDF must be 1 over x, so that the area equals 1. Let's calculate the standard deviation of the length of the second break. We have, first of all, that x is uniformly distributed between 0 and L, and y is uniformly distributed between 0 and x, where x was the distance of the first break. The first step is to compute the PDF of observing the random variable x and y. That's denoted f sub x comma y, and it's equal to f of x times the probability f of y given x. We know what those functions are, And the total is 1 over L of x, where we have the inequality that 0 is less than or equal to y, less than or equal to x, less than or equal to capital L. We can now compute the PDF of the random variable y by integrating f of x y dx. In this case, we know that x is bounded between y and capital L, so that gives us the limit of integration. If we evaluate this integral, we arrive at 1 over L times natural log of L over y. From here, we can compute, first of all, the expected value of y, which is the integral of y f of y dy. In this case, y is bounded between 0 and L, which is the maximum possible value of y. In this case, the integral is a little bit nasty to deal with. If you go through the evaluation, you'll find capital L over 4. Now, this should correspond to your intuition because the expected value of the first break is 1/2 of L, and the expected value of the second break is half of that, which is L over 4. To compute the variance, we can use the formula that the variance of y is equal to the expected value of y squared minus expected value of y quantity squared. When you do the evaluation, you'll find that that's 7 over 144 L squared. To find the standard deviation, you then take the square root of the variance, which is the square root of 7 over 12 L. In this simple example, there was still a lot of work required in order to obtain the answer. Let's see how this compares to a Monte Carlo approach. Using Monte Carlo, we only need to perform inverse sampling on two simple distributions, the uniform distribution. So you can easily compute the CDFs based on the PDFs that I showed earlier. Those are x over L and y over x respectively. You can perform your own inverse sampling, but a lot of mathematical software today like MATLAB or Python has built-in uniform sample generators. Here's what the pseudocode looks like for the rod break example. To make this more concrete, I set L equal to 1 meter. The total number of samples we're going to draw has 10,000, and then I set up an array Y, which has a length of 10,000. I first draw a sample of X from a uniform distribution from 0 to L. Then based on what X is, I draw a sample Y over a uniform distribution from 0 to X. Then I save the values into an array. I can then, based on that array, compute the variance and from there, the standard deviation. This slide shows the output of a Monte Carlo study under the following parameters. As I said before, L equals 1 meter, N equals 10,000. This plot shows the computational results. The gray bars show a histogram of the samples, which are normalized, and the blue line shows the theoretical function that we came up with. Using the sampled values of Y, the expected value from my computations, which is E hat here, is 0.25. Remember, the analytical answer was 1/4, so that's about a 0.15% error. Standard deviation is 0.22, in which case it's a 0.27% error. So as you can see, very close, even with 10,000 samples. It only took about 5 milliseconds to run the study. Writing this simple script to do the Monte Carlo analysis and analyze the results was much easier and less time-consuming than doing the calculus.